And welcome to everyone who is joining us via the recording. So section 2.6 and 2.7, we're talking about implicit differentiation, and then like rates of change is applied to like word problems, basically.
Yes.
So yeah, why don't we get started? 2.6, implicit differentiation. You do not have the same section. Right?
Yeah, that is correct. So I'm.
I think it's.
I probably. Well, I was going to say I can open it, but I.
3.5.
Okay, 3.5.
Because I have 2 copies, and I think that.
Right.
Just 3.5.
Okay.
So for both copies of the book, we are going to be looking at, sorry, let me get to the right page.
Right.
Let's just start with problem 1 and start talking and thinking about implicit differentiation, if I can find the correct problem. Okay, so problem 1, we have 3 kind of goals with this problem. We're going to find y prime using implicit differentiation.
Mm-hmm.
We're going to solve the equation explicitly for y and then differentiate to get y prime in terms of x. So this is going to be using some stuff that we did last week. And then we're going to be checking to make sure the solutions are consistent by substituting the expression for y into the solution. So that's kind of our game plan for approaching this problem.
All right.
So we have, this is on page, what page is this? This is page 166 in section 2.6 of the main book that people are using. And our problem is going to be 9x squared minus y squared is equal to 1. So if I'm going to implicitly differentiate this, what is the first thing that I'm going to do?
Well, implicit is you just start by taking the derivative of each side of the equation, right? Okay.
So that's the first thing I'm going to do.
Perfect.
And then what do I know in terms of my like rules of derivatives? If I have something that's like the derivative of something subtracted.
Sure.
I think this is...
Okay. Oh, sorry.
I think this rule might have a name, but it's basically like a subtraction rule for derivatives.
Well, it's just, well, I don't know if this is like the obvious point. It's just the derivative of the first expression minus the derivative of the second expression. Okay.
So I'm going to just write it out like that. Okay. So now we can kind of break this down a little bit further. What is going to be the derivative with respect to x of 9x squared?
So this will be 2 times 9, which is 18, times x to just the first.
Okay.
And then this is the one that like always trips me up, but this is going to be 2y to the first times y prime.
Yes, exactly.
Okay.
And then what about this?
This is just going to be equal. That's going to be 0.
Yep, exactly.
Perfect.
And so, yeah, everything's right here. So I'm going to rewrite this. I'm going to just add 2y prime to both sides.
Mm-hmm.
So I end up with 18x is equal to 2y prime. I can divide both sides by 2. So 9x is equal to y prime. Our All right, so what am I solving for in this first section for part A? Like, what is my
Well, so what else was the problem? Explicitly for y. Well, so do we want to find the y prime first? Okay, so then we'll just divide y from both sides.
Exactly.
Okay.
So I end up with y prime is equal to 9x over y.
Perfect.
And that's what I have. Okay, so we've answered part A. Now let's talk about part B. What is different about our approach with part B?
So is part B doing it explicitly?
Yeah. So we're
Okay. So if I understand correctly, the difference with doing it explicitly is we're going to get y isolated, or we're going to get y on one side first, and then essentially we just do the same thing, but with the equation set up that way, correct?
Exactly.
Okay.
So I rearrange, so I've got y squared on this one side, and I've swapped sides. So y is equal to plus or minus square root of 9x squared minus 1.
Okay.
So what am I going to do with this?
So I mean, what I think might be the easiest is change the square root of 9x squared minus 1 to 9x squared minus 1 to the 1/2, just to make that a little easier. And then don't we just apply the ddx to both sides? And
Yep.
Okay.
So now I have dy dx is equal to ddx. This is to the half. Okay. So this is just another name for y prime.
Right.
Right? And that is equal to, and then we're going to have to find the derivative of this. And this is kind of last week material. So how am I going to find the derivative of the square root of 9x squared minus 1?
This, we're going to use the chain rule.
Yep.
Correct? Okay.
So what are my functions?
Okay. So if we start, I guess we start in the inner, we could just do like f of x is 9x squared minus 1.
Okay. And that would make f prime of x.
Just 18x.
Okay. And then what's my next function?
I guess the next function would be the outer, which would be the same thing, 9x squared minus 1, but to the 1/2.
Okay. And so what do you want to call this function?
Oh, sorry. Yeah, g of x. Yeah, sorry.
Do we want to call it g of x, or do we want to call it g of something else?
Oh, I guess here we use like u in this case, or, oh, no, I'm sorry. Well, so let's go back for a second. If we said it's like g of f of x, we could just make it, I mean, yeah, we could write it that way.
So g of f is equal to what?
That is the 9x squared minus 1 to the 1/2.
Yes, but if we're going to say that f is equal to 9x squared to the 1/2, and we want to write this in terms of f, then it would just be f to the 1/2.
Oh, okay. So, I'm sorry.
yeah,
yes.
It's like nested.
Yes.
So we have 9x squared to the 1/2 up here. That is equal to f. And so I'm just going to write this as f to the 1/2.
Got it. Okay.
So what is g prime of f then going to be?
So I guess then that would just be 1/2 f to the negative 1/2.
All right. And so if I have the chain rule, if I have the function g of f of x, and I want to take the derivative of that, what is the like formula? Like, what am I going to end up with? This is like something that you had to memorize. If you don't have it memorized, that's fine.
This isn't the wait, hold on, sorry. Okay. Right. The derivative of like a function of a function is just the derivative of the function times the derivative of the, I don't know if I'm using the terminology right. Yeah, so g of f of x, g prime of f of x times f prime.
Yeah.
Of
so
x. Okay.
Yeah, we have the derivative of the outer function and outer function of the inner function, and then multiplied again by the derivative of the inner function. So
yes.
Yeah, I'm pretty sure that's what you were getting at.
I was trying to. Yes, I'm sorry. Yeah, like I was. Yeah,
g
I was
prime
getting there.
of f times f prime is kind of how I would just kind of remember it. So let's put this all together. We have g prime of f, so that's 1/2 times f to the negative 1/2, and f is equal to 9x squared minus 1.
Yes.
Times f prime, which is 18x, right?
Yep.
So I'm going to go ahead and simplify this. So that's 18 divided by 2, so that's 9x times 9x squared minus 1 to the negative 1/2. And so I can rewrite this also so that it looks like this. 9x over 9x squared minus 1. Okay, so now for part C, what am I doing?
Part C. Check their solutions to part A and part B are consistent by substituting the expressions into Y. Okay. Okay. Got it. So we have what Y equals.
We
Part
have
B. So we're going to substitute Y into the answer from part A.
So if I know that y prime is equal to 9x over y.
Sure.
And I know that y is equal to the square root of 9x squared minus 1. Now I can compare that to what I have
we
y
got.
prime. Yeah, exactly.
Got it. See, and I was like, I'm gonna be honest, I was actually like 90% of the way understanding the difference between these two, but I just thought it was, essentially two different ways of getting the same answer. I guess I didn't make the connection of substituting in this case.
Yep.
Part B back into part A to make sure that they're the same.
Yep. So that's kind of what this problem is like designed to illustrate, is that this is kind of the relationship. So I don't remember quite clearly if the book like very explicitly stated, I'm going to erase this. That's all right.
Sure.
But the different ways of like writing a derivative, for instance, if I have the function f of x and I want to take its derivative, I can use f prime of x, or I could use df dx, right?
Sure.
The derivative of f with respect to x, and that's like the Leibniz notation version. But kind of the result of like this implicit differentiation is that we are taking ddx of y of x. So we have this function y of x, and we're getting dy dx, which is the equivalent of y prime.
Right.
So sometimes the reason that there's like two different ways of writing this down is because sometimes it's just easier to have it in this Leibniz notation, because it makes it explicitly clear what we're differentiating with respect to.
Right.
Other times it's easier just to have this in the y prime because we already know what's going on here.
Sure.
So for the like purposes of this section, I'm pretty sure we're just always differentiating with respect to x, or, you know, like whatever the generic variable is, and y is going to always be the other one. But
Sure.
know that anytime you see y prime, you could substitute that with dy dx or dy dt.
Yeah. It took me a while to get that. Like, you
Yeah.
know, if you don't know what the variables are being used for, I mean, seeing dy dx at first, I'm like, you're throwing too many letters. Like, I don't know which each thing means, but I mean, it does make sense the more you work with it, I suppose.
Yeah. Yeah, I would recommend getting pretty comfortable with like the Leibniz notation, because for me at least, it makes it pretty clear what's happening.
Yeah.
Let us also do let's do problem 5. So this, we don't need to do all like 3 steps and like verify. The reason we use the implicit differentiation is because sometimes it just gets too complicated to do, like isolate y and then take the derivative. So we're going to be finding dy dx of this function. So we're still on page 166.
Okay.
And I'm pretty sure this should be in your book as well.
Yeah, that's what I thought this was, and that's it. Yeah.
Sweet. And so our goal is to find dy dx. All right. So let's kick this off. What are we up to first?
Okay, so if we're doing this implicitly, we can just, we can apply ddx to both sides.
Mm-hmm. It's kind of sloppy, but so we will end up with something, and I'm going to write this down for all of them, just because, like I said, like last class period, it makes it easier for me to like see things if I have it written down very explicitly.
Sure. Yeah, I think we went over that last week. Like, it helps to have the tiny in between steps so that you basically don't, kind of don't lose where you're at.
Mm-hmm. Okay, so we have all of these pieces that we need to determine, right, in order to put it into a final equation. Some of these we can do very easily. For instance, the derivative of x squared.
It's just going to be 2x.
We can do this pretty easily.
0.
We can do this pretty easily.
So that's going to be 2y times y prime.
2y y prime. Or dy dx.
Oh, okay. Yeah.
2y y prime dy dx. Okay, so that leaves us with this chunk here.
Yep.
Which I'm going to kind of bracket off, and we're going to do in this area.
Sure.
So we have the derivative with respect to x of 4xy, and y is a function of x. So I'm just going to write that y of x. What am I going to use to solve this?
I believe the product rule.
Yes. So we're going to, first things first, one of the rules that we can use to simplify this a little bit further is constants can be moved on the outside. So I have which 2 functions?
Oh, you mean like just like
generic,
like
so like for a product rule, I need 2 functions that are multiplied by one another. So I have.
So I guess we could just do f of x. F prime is 1. Okay, and so we can just do like g of x.
Yeah. And so what does g prime of x equal?
That's
one.
One
way that we can do this is, instead of saying that it's g prime of x, we can just say that this function is y of x, right?
Okay.
Because it is a function of x.
Sure.
And so what would y prime of x be? or y prime of x, or in this instance, dy dx, as we were saying. So instead of having a g of x is equal to like y, we can just say that we have this function f of x times this function y of x, right?
Okay, yeah.
And we're just not going to simplify that down. We're going to leave it as y because we have no thing that we're substituting in for. But theoretically, we have an equation that y of x is equal to.
Okay.
Are you okay with that?
I believe so. Yeah.
Okay.
I'm sure
Stop me.
it'll
Stop me when you're not okay.
Okay.
So then we have a product rule, which is going to be if we have a function f of x times y of x, which is what we said we had here, the derivative is going to be equal to f prime times y plus y prime times f.
Yep.
So we can write that out. We have f prime, so that's 1 times y, which we're going to just leave as y of x, or just y, plus y prime times f, which in this case is going to be x. So this is going to be ddx of x4 times ddx of x y, which is a function of x, is equal to y plus y prime x. And then what do I need to bring over?
To make sure that we're multiplying that by. Yeah.
Yep. So I'm going to move this back over here where it belongs.
Sure.
And I'm going to say that this is minus 4y plus 4y prime x.
Got it.
So we can just step down. Now it's kind of algebra from here on out. We just need to make sure that this makes sense algebraically. We'll have 2x minus 4y minus 4y prime x plus, we're here. Rather than saying y prime, let's rewrite that in
dy dx.
y dx plus 2y dy dx is equal to 0. What am I going to do next?
So I would keep everything that has dy dx on the left and move everything else to the right of the equal sign.
So I'll have negative 4x dy dx plus 2y. This is kind of another, I don't know, pro tip. If you're using dy dx instead of y prime, it's really easy to see.
It's easy to see what has that as yeah.
Like you're not missing any terms.
Sure.
It's very obvious. All right, so next step.
We can factor out dy dx and have that multiplied by the sum of negative 4x plus 2y.
And finally,
we can divide that from both sides so that we're left with dy dx.
And that's our answer.
Yeah, like I realized because I was doing some practice, like I try to do 1 or 2 of these like a day, and it's actually helping a little bit. And the thing that like I realized that you mentioned earlier is like once you figure out what the derivative of like each of these polynomials is, it's just algebra after that. So it's really like as long as you can do algebra, you've done the heavy lifting.
Yeah,
at the
once
beginning.
you get past that like first stage. So yeah,
Cool.
that was that. Let's try one with trig. Let's do number 11.
Oh, sweet.
So I think that should be in your book too.
Y cosine x
Yes.
equals.
I should probably write it down for you beforehand.
Oh,
Yeah,
that's all good.
Y cos x is equal to x squared plus y squared. All right. Again, we're trying to find dy dx.
Yes.
So first things first, let's take the derivative of both sides.
Yes.
So we'll end up with ddx y cos x is equal to dx x squared plus ddx y squared. All right, so these two we can get pretty easy. So this is going to be 2x plus 2y dx. This one, we're going to need to take a sidebar. So what rule am I going to be using to solve this?
I think just product rule.
What are my two functions?
So we have y and we have cosine x. Okay. I'm sorry. You said functions.
Yep. No, my two functions are y, and then I have f of x.
Sure.
Cos x. So f prime of x is equal to what?
That is negative sine x.
Bingo. All right. So if this is y times f, our product rule says that we're going to have y prime times f plus f prime times y.
Yep.
So we're going to end up with y prime times cos x plus negative sine x times y. Or to put it a little bit more simply, y prime cos x minus y sine x. All right. So now we can take this and put it over here. I'm going to write it as dy dx cos x minus y sine x. And we are good to go for some algebra. All right, so dy dx cos x minus 2y dy dx is equal to 2x plus y sine x. We can factor out that. And we can divide. So we end up with dy dx is equal to 2x plus y sine x over cos x minus 2y.
Fantastic.
All right, and that should be our answer.
So and I do follow that. I have a question before it escapes me. I remember doing something when it's when we're trying to find the derivative of a trig function. I remember seeing an example somewhere where like if it was like sine theta, just as an example, like you take the derivative of sine theta and then the derivative of theta. Is that like it gets broken down further than just sine theta? It's sine theta and
well, if you want to consider this like a chain rule type problem, right? Then what we would say is that we have, like, if you want to say that this is like a function theta. And we're using theta. This is a function f of theta.
Okay.
You would be able to say you had like your first function we'll call g of okay, so we'll call, yeah, I guess we could call this g of theta is equal to just plain theta, right? So that's our internal function.
Sure.
So g prime would be equal to 1. And then we have h, which is equal, h of g, which is equal to sine g, and then h prime, which is equal to
cosine g, okay.
G, right? And then you would be able to put it together because if you were to have a function that is structured like this, you would say that the answer would be h prime of g, right?
Yeah.
Times g prime.
Right, times h. Or, oh, no, I'm sorry. No, I'm sorry, that's it.
Because this is the chain rule.
Right.
So if we're using the chain rule to solve this type of problem, we would end up with the cosine of g, which is theta, times g prime, which is 1. So we'd end up with cos theta.
So, it might, I think it's occurring to me now that, so in the case of like the previous example, since the derivative of whatever it was the sine of was just 1, we kind of just disregard that because it's 1.
Yeah.
I think in the cases where it was like sine theta squared, that's when there was actually something remaining after.
If there's a squared here, then that's different.
Right.
If I remember doing this last time. If there's a 3 here, then this goes from here. So keep the peach 3. So what changes here? We now have g of theta is equal to 3 theta, right? And so g prime of theta is equal to 3.
Oh, okay. Right. Got it.
Our end result will be 3 times cos 3.
Got it.
So we were talking about this in terms of there was an unofficial / official rule that if you had something that was structured like this, like if you had sine of 4x, then the derivative of this would be 4 cos 4x. You would just pull out that constant and move it out.
Oh, that's right. Right. So you're not moving it. You're just like taking it and also placing it at the beginning.
Exactly.
Or like at the front of it as a coefficient. Okay.
Because we're using the chain rule, and that's how the chain rule would work.
Okay.
So if I were to take the derivative of 4 sine or 4 cosine 4x, I would know that it was going to be 4 times 4, so 16 negative sine 4x.
Okay.
Negative because we're going from cosine to sine. 4x stays the same. This is 4 times 4.
Okay. Got it. That makes a little bit more sense context wise. Okay. Sorry to go on a tangent.
No, that's fine. That's what this is kind of for.
Sure.
Okay. So that kind of makes sense?
Yes. Yeah. I follow now. Thank you.
Do you want to move on to section 2.7 to do some of these like word problems?
Yeah, please. Yeah, because those tend to, make me think a little bit more than.
These trip me up.
Yeah.
Right away. These are the kind of problems that kind of stress me out, but they are also a favorite on exams. So,
yeah. Well, isn't that convenient?
Yeah, of course. Just wait until we get to like optimization and stuff like that. That's a real treat.
Great. Can't wait. Yeah.
Something to look forward to.
Sure.
So we're going to be on page 178. And we are going to start with problem 5, and we're just going to do A. But we have here a graph that I can sketch out. A graph that looks like this. This is 1.
Okay.
here. So this is t. So this is a graph of a velocity function where t is measured in seconds. And the question is, when is the particle speeding up and when is it slowing down? So we need to assert what we have and what we want and then figure out how to get where we need to go. So what do we have based off of what the problem gave us?
Well, so I don't know if this is like the first step, but I was really struggling with this week. And the one thing that kind of helped me was, I guess, finding the, for lack of the proper terminology, like the plateau points. So where basically the velocity, I think, would equal 0. So kind of at the crescents of the...
Okay. The question is that where the velocity equals 0? Because what we need to ask ourselves is, what graph is this? The problem as it is framed to us right now is that this is the graph v of t.
Okay.
So this is the velocity graph.
Oh, I'm sorry.
So the velocity graph equals 0 at these 2 points. So at 0 seconds and at 2 seconds, the velocity is 0, right?
Maybe I was thinking of the acceleration.
Yeah. Okay. So what is acceleration? That's a good place to start. What is acceleration?
So that'll be the derivative of velocity.
Yep.
Which I think, and obviously correct me, but I think that's maybe what I was trying to get at is the points where there is no slope. Right. Okay.
That's really a of 1. So here we have no slope. So our acceleration is equal to 0.
Right.
Now we can go back to the beginning of the question and ask what they really want.
Yes.
They want to know when each particle is speeding up and when it is slowing down. So we need to ask ourselves, what does speeding up mean? In terms of math and like the language that we're using.
Sure.
So what do you think, how can I describe speeding up in terms of the math language that I'm using? So
let me see if I remember this correctly. Speeding up is when both the acceleration and velocity share the same positive negative value. So if the acceleration is a positive value and velocity is a positive value, then, or if they're both a negative value, it is speeding up. I don't know if that's
a good way of looking at it.
Okay.
Unfortunately, this is like one of those times where language kind of fails us. I would say that speeding up is let's see, I'm trying to think of a good example. When I was looking for this problem, I said that when speeding up, it's speeding up when the acceleration is positive.
Okay.
But at the same time, you're completely right in asserting that it is like speeding up in the negative direction when both the acceleration and the velocity are negative.
Okay.
But I would kind of say that it's speeding up in a positive direction. So speeding up in a positive direction is when the acceleration and the acceleration is positive.
Oh, so are you saying when moving forward versus moving backwards?
Yeah.
Okay. So when the particle is moving forward and the acceleration and velocity are positive.
Well, no, I just went ahead and said that it's speeding up when the acceleration is positive.
Okay.
And it's slowing down when it's negative. But I really like the way that you thought about how the velocity will impact it. I think that's a really good step to like take. And it's like, it's an issue because I'm not entirely positive what exactly they want from this problem. Because it's just asking us to figure out where it's speeding up and slowing down.
Sure.
I answered the problem was I said that it's speeding up when the acceleration is greater than 0. So where is that in this graph?
Okay, so the acceleration is going to be the derivative of velocity. This is the graph of velocity. So the derivative of velocity being the acceleration is just going to be the slope at any given point.
Mm-hmm.
And the slope is going to be positive if the slope is going upward. Right.
So, yep. So this
Okay.
is where I said it was speeding up.
Okay.
I said that from here to here, I'll put that in a different color, is where it is slowing down.
Okay.
So that was my answer. We can take it up a notch and think about not speeding up as like positive acceleration, but speeding up in the way that you defined it, where both the acceleration is greater than 0 and the velocity is greater than 0. And I think this is probably going to give us a better idea of what is actually happening. Physics is not my thing. Anytime that there's a particle, I start to panic.
You're like, all right, problem 5, particle, darn it.
Yep. Mm-hmm. So that is kind of my like giant hang up here. So if we say that this is the conditions for speeding up, so I wrote acceleration is greater than 0, velocity is greater than 0, acceleration is less than 0, velocity is less than 0.
Right.
And then I'm going to explicitly state that slowing down is when if acceleration is greater than 0, velocity is less than 0. And when acceleration is less than 0, velocity is greater than 0. So now we need to break this graph not into 2 parts, but into 4 parts, where all of these conditions exist. So,
so the x-axis is t. Is the y-axis is that part I was.
It's velocity.
Okay, so okay. The y-axis is velocity. Okay, got it.
So as t increases, like from here, from 0 to 1, for instance, as t increases, velocity is increasing.
Got it. Okay.
So we already established some things. First of all, we said from here to here, acceleration is greater than 0. And then from 1 to 3, so from 0 to 1, acceleration is greater than 0.
Yep.
And from 1 to 3, acceleration is less than 0. So really what we have is we have 3 distinct parts, and we've marked those all out with these blue and green dots, right?
Mm-hmm.
We have a part from here to here where acceleration is greater than 0, and we're above the x-axis. So what does that correlate to? Speeding up, slowing down? Which one?
I'm sorry, phrase that again. Sorry.
So from 0 to 1.
Oh, okay.
My acceleration, I said, is greater than 0, and my velocity is greater than 0, because I'm in this positive zone right here, right?
Yes.
So am I speeding up or am I slowing down? If they're both greater than 0.
Well, according to the math, I want to say that we're speeding up.
Mm-hmm.
Okay.
Exactly. So I'm just going to kind of outline this in the green, and I'm going to put an arrow there. I'm going to call it speeding up. And I can say from x is equal to 0 to x is equal to 1, the acceleration is greater than 0, and the velocity is greater than 0.
Mm-hmm.
And that is true. And so I'm speeding up. So starting at 1 to 2, I have this area where my velocity is positive, right?
Yeah,
But my acceleration is negative.
correct.
So what does that correlate to?
So we are slowing down.
Mm-hmm. So from x equals 1 to x equals 2, I have an acceleration that is less than 0 and a velocity that is greater than 0.
Mm-hmm.
Because I'm still in this positive zone up here for velocity. So I'm going to cover up that line with this other green. And I'm going to say that this is slowing down. All right. How about this last condition? Here I have acceleration that is less than 0 and velocity that is less than 0.
So it is speeding up.
Yep.
Yeah, okay.
So from x is equal to 2 to x is equal to 3, as I said earlier, acceleration is less than 0, velocity is less than 0, so I'm speeding up as we defined earlier. All right, so the real takeaway from doing this is we need to be able to define what we're looking for in terms of mathematical concepts. So here we characterized speeding up and slowing down by describing acceleration and velocity.
Mm-hmm.
And that is how we found an answer. And we divvied it up, as we talked about earlier. We picked out 0 points. Where does the velocity equal 0? Where do we transition from positive to negative velocity?
Sure.
Where does the acceleration equal 0? Where do we transition from positive to negative acceleration? Because we can't go from positive to negative without crossing 0, right?
Yeah.
So identifying those zeros was a great first step.
Cool. All right.
You sound very tentative.
I,
Are you on board with this?
So this is gonna sound like
No.
it's just weird right now because on yeah, I totally 100% understand the mathematics of what you have up right now.
Mm-hmm.
For whatever reason, I'm trying to think of I'm having cognitive dissonance right now. I'm thinking of if a particle started at the time 0
Mm-hmm.
and we stop at point 1 in time, so 1 second, and the acceleration, so the slope at any given point is
Mm-hmm.
leveling out at second 1.
Mm-hmm.
So would that mean that it is speeding up? It seems like it's slowing down up to the second 1 in time.
Okay.
Do you see
Yeah,
that's
no, I see exactly what is slowing down is the scale, perhaps. So the velocity is, I'm not going to use the word slowing down anymore because
okay?
we need to divide that language up.
Sure.
So we establish what speeding up and slowing down is now. So now what we need to talk about is relative velocity and relative acceleration.
Okay.
So if we take the derivative of velocity, we have acceleration. And if I were to sketch out, for instance, so if I were to sketch out right here, I have, this is what my tangent line to the curve is.
Right.
And so that's pretty positive, right?
Yeah.
And if I were to go from here, it's much less positive, right?
Right.
At this point. And then if I were to go here, it's 0.
Yeah.
So we established that my acceleration is positive at all of those points, but it's becoming less and less positive.
Correct.
That doesn't mean that it is not positive. Let's go ahead and draw the acceleration graph because we can do that.
Okay.
So if I were to, I'm going to erase this and then all of this because we established what's going on here.
Sure, yeah.
we're okay with all of that.
Yeah, yeah.
So if I were to have an acceleration graph, it would look something like this. I would have acceleration is equal to 0 where?
Oh, so if it's the, well, I mean, 0. Well,
Where is
oh no, I'm sorry, 1. Yeah, I'm
Yeah.
sorry, 1 and 3.
Yeah. So it looks like it's planning on curving back up. So we can put a dot there. And
Sure.
at 3. It's 2. So what is this graph going to look like? This is like back to like drawing derivatives. So we have the zone here from 0 to 1. We know that acceleration is positive, right?
Yeah.
And is it more positive at 0 or more positive at like 0.75?
Well, it's basically less positive.
Yep.
After 0.
So it's going to look like this, right?
Yeah.
Because
Yes.
it said that it was going to be more positive here, larger slope, more positive than here.
Yeah.
0.
Okay.
Okay. So we're cool with that.
Yes.
Now we have this point where it is we have an acceleration that is less than 0, so we know we're going to be negative, right? And we kind of, I mean, like this graph looks like it's going to be curving back up, and I can kind of see an inflection point at x is equal to 2. It's important to note that just because it crosses the x-axis does not mean like that crossing the x-axis, this blue point here with this velocity, that is not what gives the inflection point. The inflection point would be there regardless. If we moved it up, if we moved it so that it looked like this, then the inflection point would still be right here, right?
Yeah, got it. Right.
So, do you know what I mean by inflection point? Did they cover that vocabulary?
I don't think so, but like in layman's, can I say like that's like the point at which it's starting to change?
Yes, okay. Exactly. So we start here and it's less positive. We go here, it's more positive. The point at which the slope is the most positive is going to be that inflection point.
Right.
And then from the inflection point onwards, so less positive, more positive, most positive, less, or negative, excuse me, less negative, more negative, most negative, less negative, less negative.
Got it.
So it's most negative at the inflection point. So we'll call that like right here. And so it comes around like this. So it's approaching its most negative point at x is equal to 2. And then it's approaching 0. We're going to say again, we're pretending that there's a 0 point there, even though it's not really clear. We're going to extrapolate from the graph.
Yeah.
So we have something that looks like this for our acceleration graph. Are you comfortable with saying that this is a good acceleration graph?
Oh, yeah. Yeah.
Okay.
I'm on board.
All right. So it's not that we are, like it's not that the particle is slowing down. Like as we described, like the slowing down, the acceleration is still positive in between, like you had issues if you're like approaching like t equals 1, right? How would it be speeding up if the acceleration was slowing down? Well, the reason this is happening is because the acceleration is still positive and it's still like increasing in velocity. So velocity is increasing, it's going in the positive direction. It's just not increasing as much at second t equals 0.75 than it is at 2.5, for instance.
I think I might like get what my hang up maybe was. Like the speeding up, I think I was taking as it is getting faster,
Mm-hmm.
which I think there might be a differentiation between.
Well, if we take faster as velocity, right, increasing velocity, then it is getting faster because the acceleration is positive. It's just not increasing acceleration.
Okay.
It is getting faster, velocity is increasing, but acceleration is not. I
like this is gonna sound really weird, but like if you just told me like do like the math on the paper, like I'm there. Like I think if it probably doesn't help. It probably doesn't help me to think of like in the real world what this would look like. I can figure it out on paper. It's just really weird. Like if I don't think about the real life of it, I can get it.
This is where I struggle with physics. So I don't know. Are you taking physics 211?
Because I'm going for software engineering, there will be 2 physics.
Are you taking 211 or 250?
211 sounds more like I've mapped this out. I don't remember which one it is, but 211 sounds more appropriate than 250.
Okay.
I think 211 probably.
So yeah, that's the calculus-based one.
Cool.
And yeah, no, physics is like I'm all on board with math, and then the minute physicists get their hands on it, I just lose track of everything.
Yeah,
it's the most confusing thing ever.
In theory, like I think maybe I take very simple things for granted. Like I can watch like gravity work, but like if you try to like if you try to mathesize gravity, like
I keep thinking about gravity, right? And if we have like an acceleration, so gravity is an acceleration, right? So if we throw a ball even just like straight up,
sure,
so we start and we throw it up, right? Then gravity is going to be acting as a negative accelerant.
Sure.
So if we graph the velocity of that ball, the velocity is going to be...
It's fine. This is like literally one of the problems. This is like
okay. So I'm gonna try to get this right.
Sure.
The velocity has an initial velocity that we throw it at, and then decreases. And the velocity hits 0 at some point. Actually, this is exactly the problem that I was planning on doing next.
That's crazy.
We're gonna do number 7 next, by the way.
Sure.
Which is this exact thing. So I'm just gonna write number 7 and pretend like I'm doing the problem.
Isn't that great how everything just works together?
I knew this looked familiar. Okay.
Yeah.
So number 7, we have a ball. And we're tossing it straight up, right? So we're tossing it from a height of 0, we'll say, basically. Assume that we're tossing it from a height of 0.
Oh, this one, I don't know if we want to do 7. It does say shot vertically upward from a point 2 meters above ground level.
Okay, that's fine. We can.
Will we call that 2? Will we call it 2? Or?
No, we'll make that work.
Oh. No, I just want to make sure I was on board.
Yeah, no. So we'll call this, we'll just make this like a y-axis for height, basically.
Okay.
And so we'll toss it from 2 meters, and here is 0 meters.
Okay.
Right? So we're imagining this ball, and we're tossing it upwards, and it reaches its max height, which we'll call that HM. And then the ball will, this is not a time graph.
Sure.
This is just a line on the bottom. And then the height, it will come down. So if I were to draw this as actual like time, if I were to graph where this ball was at certain points in time, so this is kind of like a S of t, like where is the particle being? Like
sure.
I would start here. I would reach the height, the maximum height, and then it would come down to the ground. So it's like a parabolic shape. I have a maximum height, that occurs at a time that is, I don't know what I want to call this. We'll just call it T1 for now. I have this, which is the final time the ball is no longer in the air. And this is kind of like what the position graph is going to look like, right?
Yeah.
Then I also need to think about what velocity is going to look like. So if I have a velocity, I'm going to have something that looks a little bit something like this. I have a parabolic shape. So what shape do you think my velocity graph is going to be? The derivative of my position is going to be what kind of a graph shape?
Wait. So, okay, the first graph is like the position of the particle.
So if I say that S of t is equal to x squared, what would b of t be?
Oh, 2x.
So
That's
this is not exact, but this is kind of how I think about, like, if I have to graph something.
Okay.
I'm graphing a derivative here, right?
Yeah.
And I'm graphing the derivative of a parabola, which is always going to give me a line.
Right.
Because regardless of what other junk I have in terms of constants and y-intercepts and all of that jazz, I'm always going to end up with a line if I'm taking the derivative of parabola.
Okay.
So I start off with a certain velocity, which I'm going to call vi. It's going to decrease until I hit this, which is t1, which is where I am at my peak. And then it's going to decrease even further. And then it's going to, abruptly jump to 0 because it's not moving anymore. We'll just have it decrease until t. All right. So this is where we are right now. We've kind of sketched out what's happening here. We have a max height, we have a time at which we hit the max height, we have a time at which we hit the ground, and then we have a linear velocity. So now let's think about what the acceleration looks like. If I have a straight line, what is my acceleration going to look like?
The straight.
I have this.
Oh, sorry.
Linear function.
Got it.
So.
It's the derivative. Well, the derivative is going to be the slope of the velocity. So it would be the same line. Right?
Would it be the same line? What is the slope of that line?
Well, the one that's drawn is negative something.
Yeah, it's actually
like negative x or negative. Yeah. Negative 2x.
It'll be, well, because as we'll determine later, it's gravity that's the accelerating force here. So if I were to take this, generally speaking, I have this graph, which I'm going to call some sort of parabolic function.
Sure.
This is not precise, obviously, but I'm going to call it kx squared. I'm going to take the derivative of that to get the velocity, which is 2kx. That's how I know that I'm going from a parabola to a linear function. Now, if I'm going to draw a of t, I need to take the derivative of this, which is going to be what?
2.
2k, but yeah.
Okay, 2k, okay.
I'm just going to keep on that function. So this is going to be a flat line with a slope of 0. And it's going to be right here at negative 9.8 because that is the acceleration of gravity. So if we were to take a physics approach to this, we would say we have a ball that is going up because we forced it to go up and we have an initial velocity. But after we let go of the ball, there are no forces acting on it but gravity, which is forcing a negative acceleration, which basically means that even though we threw it up, gravity is constantly pulling the ball down and eventually it will hit the ground.
Got it.
So regardless of whether or not the ball is going up, after we let go of the ball, which is what we called like t is equal to 0,
Mm-hmm.
the acceleration will always be negative.
Okay.
Okay. So, this position is small. Okay. So we have these 3 lovely graphs that kind of demonstrate like what's going on. Now we actually should look at the problem. We are given this equation. H is equal to 2 plus 24.5 t minus 4.9 t squared. We know that VI is equal to 24.5 meters per second. So, part A, we need to find the velocity after 2 seconds and after 4 seconds. How are we going to find velocity?
Well, okay. Since velocity is the derivative of this first equation that it gave us,
Mm-hmm.
so if you first find the derivative of that, so h prime of t.
So that's equal to 24.5 minus, what is that, 9.8, I think? Yeah, 9.8.
I think it sounds right, yeah.
9.8 t.
And then we're just going to first plug 2 in for time, and then 4 in.
So break down this equation for me. What's going on here?
So we've punched in 2 for time, and then we're going to sub that in for t, and the same for 4. And
in terms of numbers, though, here I have 24.5. So if I took v of 0, my velocity would be my initial velocity.
Sure.
So that's a good way of just making sure that I'm like, I did something right.
Oh.
Right?
So, to make sure you set yourself up properly,
yeah.
to just go by that little benchmark.
So I know that my initial velocity at t is equal to 0 is 24.5. So if I take v of 0, it's 24.5 minus 0.
Got it.
So yeah.
Okay.
And then we can also see here we have gravity at 9.8, negative 9.8. So that's how gravity is affecting.
Oh, gotcha.
So
because if you look at it like in actuality, like the more seconds that go by, gravity is exerting more for it's bringing it.
Bingo. That's
down.
Exactly what's happening.
Okay.
As t gets larger, what's happening? That's
got it.
Exactly.
Okay. Cool. That part I follow that now.
So I am typing this into a calculator right now.
Okay.
So this should be what, 4.9? So this is 4.9, and this after 4 seconds is negative 14.7. So, and what units are these 2 values in?
Well, so this is in,
it's velocity.
It's velocity. So, meters per second.
Mm-hmm.
Okay.
Cool. So that was part A. All right. So part B. When does the projectile reach its maximum height? All right.
Ooh, sorry.
So we are looking for what are we looking for in terms of what I've written down?
So sorry. Okay. So we want to find where it reaches its max height. So it reaches its max height when it changes directions, which if we symbolize that on the graph would be basically a flat, like a flat line.
Yeah, we have this point here, which is Tm comma Hm. But what are we looking for in particular? Like, what is this problem asking us for? Like, in terms of the language that we've decided.
What was maximum height when? Sorry, are we on B?
Yes, we're looking for the time of the maximum height.
Right. So, at what point in time does it reach?
Yes.
Its max height,
which I called Tm, time of max, T sub m.
Okay.
So we're looking for the time at which it reaches its maximum height. Now, back to what you were saying about when that happens. It's when, right here.
Velocity is 0.
Exactly. So when v of t is equal to 0, t is the maximum height.
Right, okay.
All right. So how am I going to find this?
So we want the velocity to be set to 0. So in this case, can we just use the same, the derivative of, so we found the derivative of h of t. So we're just going to set that to 0, equal to 0. Okay.
Precisely. So we'll end up with 24.5 is equal to 9.8 t. So, and this, as we decided earlier, is Tm.
Yeah.
So Tm is equal to 24.5 divided by 9.8, which I'm going to punch into my calculator.
Yeah, I can't do that.
9.8. Fortunately, you're not going to have to do this in an exam because they don't let you have calculators on an exam.
Yeah, that's
not going to give you a problem like this.
You know, I was really excited at the beginning of calculus because it said it's like you won't need the calculus. Like, sweet, awesome. And then all of this like physics stuff happened. And,
well, they might give you a problem similar to this, but with easier numbers to work with. But you won't have to worry about like numbers like this because that would be atrocious.
Yeah. Something that you can easily do. Like, it's not like decimals you could do.
All right. So now we have the time at which we hit the maximum height. Part C is asking us for the maximum height, which is going to be what? H sub m is what we called it.
Sure, max height. Okay, yeah.
So how do I find h of m?
All right. What is the maximum height? I remember how I did this. I don't think this is maybe not the desired method. I took the original h of the function h of t 2 plus 24.5 t, and I set that to 0. And then I think I set it to 2, and I found the point in the middle. No, I'm sorry.
Well, if you, so we know when h is equal to 2, right? H is equal to 2 at 0 and then at some other point here. And we know that h is equal to 0 at this TF right here, we said. So in order to find where it equals...
set t equal to 0?
If t is equal to 0, then h is equal to 2. Because we have this point right here that's 0, 2, right?
Yeah.
So what do we have? What did we just find? We just found Tm, which is what?
We found when the point is at its maximum height, so we can just plug this back in to find the distance that time gives us.
Exactly.
Okay. All right. I'm back on track.
Yep. So I'm going to plug this in, and I'm going to get h of m is equal to, let's get my calculator working, 2.5. Sorry.
No, that's all good.
Plug all this in. Okay, so I got 93.88. All right. Another thing that we can do really quick is we can go back and compare A and B, just to make sure our answer in part B makes sense.
Okay.
We know that somewhere between 2 seconds and 4 seconds, we hit our maximum height, right?
Yes.
So we know that our t, or the time of our maximum, has to be between 2 and 4. And so it makes sense that we have 2.5, which is between 2 and 4.
Yes.
Another thing that we can look at is the magnitude. We're saying that this is a parabola, and it's kind of like basically like symmetrical if you fold it along that middle line, right?
Yeah.
And the velocity is equal to 0 at Tm, or the time of our max. So at v of 2, the velocity is 5. And at v of 4, the velocity is negative 15. So we're thinking that it's probably going to be closer to 2 than it is to 4. Because the velocity at 2 is closer to 0 than the velocity at 4.
Yes.
So that's just kind of how we know that our answer for part B makes sense.
Got it. Okay.
All right. So for part D, when does it hit the ground? So now we want to find what you were discussing earlier.
Oh.
We're looking for that final time. And so what equation could we use to find this final time?
So, let me see if I can get this. When does it hit the ground? Okay, so can we use V of t equals 24.5 minus 9.8 t and sub in? No.
Because we don't know what the velocity is when it hits the ground. But we do know what the height is.
So if the height...
The height when it hits the ground.
Oh, okay, 0. Okay,
yep.
So do we set 0 equal to the initial equation?
Mm-hmm.
Right. And so okay, this is, I think when I was doing a problem similar to this, I did it kind of in a reversed order. So what this will do is this will give us 2 values because there's a square, and then we're just going to choose the larger value because time is linear. So,
and our other intercept would be negative.
Right, yeah,
so
exactly.
If I dotted out that line, it would be negative, and I can't deal with negative time.
The start, yeah, we're not getting into like experimental physics, yeah. I think the problem I had too, it did not start, like it didn't give the preface of it's starting at 2 meters. It was just like it's starting at 0 meters and it ends at 0 meters. And so if this was easier to determine, like, okay, we set it to 0. We'll find 2 numbers, the bigger numbers, obviously, when it comes back down.
Okay, so how am I going to solve for this?
So we will first I'd move 2 over to the other side.
I wouldn't do that.
Oh, you wouldn't do that? Oh, okay.
I would just use the quadratic function.
Oh, we can rearrange that, yeah.
Yeah. I don't, I could not do this. So I would say, I don't know if you remember the quadratic formula. I hope I do. I'm pretty sure it's negative
it's
e
plus or minus square root B squared
4ac.
minus 4ac, yeah, over 2a.
Yep.
Oh boy.
So I keep squishing my book further and further. Okay, so this would be negative 24.5 plus or minus the square root of 24.5 squared, which I'm going to punch into my calculator.
Yeah, I don't know that one.
5, which cannot be right. Is right. We're going to just call it 600. We're going to round.
Sure.
Minus 4 times a, which is 4.9, or rather negative 4.9. This is going to end up being plus 4 times 4.9 times 2, which is c. This is plus 39.2 all over negative 4.9 times 2, which is 9.8. Okay. So the square root of 639 is 25.275. So here we have negative 24.5 plus or minus 25.275. 278, excuse me, 278 all over negative 9.8. We're going to scrap that that positive sign. What we're going to do is we're going to say this is 24.5 minus 25.278, or
right.
Yeah, so that's
to give us, because we want the bigger number.
We're gonna, because we've got that negative sign in the denominator, we're going all in on that negative.
Yeah.
278. So negative 49.778 divided by negative 9.8, and we're going to end up with 5.08. That is going to be our TF.
When it hits 0.
Mm-hmm.
Okay. Man, they really did. They gave an ugly set of numbers to do that one.
Yep. Okay. And then our final question: what is the velocity that it hits the ground with?
With what velocity does it hit the ground? Oh man.
Well,
is this where like a limit might?
We don't. Nope, we don't need that, because what do we have? When does it hit the ground? We have velocity.
When does it hit the ground?
Yeah, we have a velocity as a function of time. So we can find velocity as long as we know when it hits the ground.
Oh, got it. Okay, well, we'll see if we... Well, about 5 800ths of a second.
Yes, exactly. 5.08 seconds.
But wouldn't that technically be when the velocity is 0 because it's already hit the ground?
No, this is the velocity as it's hitting the ground.
That's what the 5.08 is. Okay.
If you see this graph that we have up here for velocity, this is the velocity as it hits the ground. So this is going to be some point, the velocity, the final velocity, or the final time, final velocity.
Okay.
And then from here on out, the velocity is 0.
Okay.
But this is the velocity at which it hits the ground.
Got it. Okay.
So the velocity is not quite 0 yet. We're getting there. This is going to be 24.5 minus 9.8 times 5.08, which I will plug into a calculator. And it will be minus 8 times 5.08, negative 25.284.
So it's meters per second. Mm-hmm. It hits the ground. Okay.
So, yeah. Do you have any questions about how this problem just played out?
No. Looking at it as a whole, it's a little bit to take in, but I do, once again, to go back, like on paper, I think I get it for the most part. Just knowing which one is the derivative of which kind of helps.
Yeah. So it's just
build the framework.
Yeah. It's this is the really tough type of problem to work through.
Sure.
Because it's difficult to figure out exactly what you need and when you need it.
Well, and since we're dealing with time and velocity and acceleration, and they're asking different things at different points, you kind of have to know which function you're taking.
For me at least, one of the things that I do, if I have time, like first thing I will do, I'll kind of make like a bank for myself of things that I have. So I'll say like I have this function h of t, and this is
right.
I'll have, once I find v of t, I'll just put it in my little like have bank, and it's like a bank of things that I have.
So that you don't have to go back through the problem and try and pull out like, where did I get this answer?
Exactly. And if I can graph it really easy, like we just did up here. We have this parabolic function to show position over time. We have velocity over time. We didn't really need acceleration over time, but it was good to make that point about gravity. But basically, that's like kind of the steps that I would take to solve the problem is graph it out, figure out what you have, figure out what you need to get. Like here, we said we needed TF. What does it mean to need TF? Well, we know that TF is the time at which the height is equal to 0, so we can set height equal to 0.
Sure.
Kind of make those steps.
Yeah, that works. I did end up watching a few videos of Krista King. Is that her name?
I'm not sure.
Well, it's the professor recommended videos. I guess she has this YouTube channel and did the same thing. Like as she's going through, like makes those bank of things on the side, and it does. It helps. It helps a lot.
Yeah, and so a lot of this class is just keeping track of what you have.
Yeah. So I've noticed that. So that does.
Yep.
It does help.
Do you have any other questions?
I don't think so.
Okay.
I practiced a lot more this week, so
awesome.
A lot of it clicked a lot more. So I appreciate it.
Awesome. Okay. Well, that's about all I have for you tonight.
That's great. Thank you.
Yes. I hope you have a wonderful evening.
Thank you.
Hope you had a good weekend, and we'll have a good week.
I'll
see you next week.
Same goes to you, and we'll see you next week as well.
Have a wonderful night.
All right. You too. Thanks.
Bye.
Bye-bye.